Solving equations, the balance method. One of the biggest problems students have with algebra is that they ignore some of the strategies and tips they are given early on. They usually do this because they think they don't need these strategies, but in time it catches up with them. It's true that you don't need a fancy method to find the value of e in this equation. But when it comes to finding the value of e in equations like this, you will need a better strategy than guessing and checking. We use the name the balance method in algebra because what we do is a lot like using a balance or a teeter-totter. The equal sign is the center of the balance, and we see that whatever we do to one side of the equation, we must do to the other side to keep it even or balanced. But let's back up. Why are we doing this balance thing? The whole point is to find out the value of our variable. We want to know if x equals 4, or if m equals 12, or if a equals 3 over 2, etc. And to do this, we need to have just the variable on one side of the equal sign with everything else on the other side. We need to get x or m or a or whatever our variable is all by itself. And to get the variable all by itself, we need to get rid of everything else that is with it by adding, subtracting, multiplying, dividing, etc. in a balanced way. If we had a teeter-totter that was balanced and we wanted to keep it balanced, we could only change one side if we changed the other side by exactly the same amount. Here something was added to one side but not added to the other side. The teeter-totter was not balanced and this is not equal. Again, if you start with a balanced teeter-totter, you have to manipulate each side in exactly the same way to keep things even and equal. If you take a pig from one side of the balance, you must take a pig from the other side. Wolverine for Wolverine. Iron Man for Iron Man. R2-D2 for R2-D2. Let's try some examples using this balance method. A minus 4 equals 8. If we add 4 to the left side to get 0, we must add 4 to the right side. We will get A equals 12. What about this? A divided by 4 equals 8. We can also write that as A divided by 4 or A over 4 equals 8. The opposite of dividing by 4 is to multiply by 4. So if we multiply by 4 on the left, we will only have A left. But if we multiply by 4 on the left side, we must also multiply by 4 on the right side to keep things balanced. We get A equals 32. What about this? 4A equals 8. This means 4 times A equals 8. The opposite of multiplying A by 4 would be to divide by 4. But if we divide by 4 on the left, we must divide by 4 on the right. We get A equals 2. What about this? A plus 4 equals 8. The opposite of adding 4 to A would be to subtract 4. So we will subtract 4 from each side of the equal sign in a balanced way, and we will get A equals 4. What about this? The square root of A equals 8. Well, the opposite of square rooting a number is to square it. So if we square the left side, we can square the right side, and we will get A equals 64. The square root and the squaring canceled each other. What about this? A squared equals 8. The opposite of squaring is to find the square root. So if we find the square root of each side, we will have our answer. A is also equal to the negative square root of 8, but we'll learn more about this negative part later. So far, all of our examples have only had one number that we've needed to get rid of, but we can have two or more terms and multiple steps. When we have more than one term and we have multiple steps we need to complete to get our variable by itself, it is often easiest to follow the Bedmes order, but backwards. SAMDEB. The S and A add for subtracting and adding. Can you add or subtract a term from each side? The M and D stand for multiplying and dividing. Can you multiply or divide a constant from each side? E stands for exponents. Are there exponents you can get rid of? But remember that square root is a 1/2 exponent. B, brackets. Are there brackets you can deal with? Let's try it out. A divided by 2 minus 4 equals 8. SAMDEB. We'll start with adding and subtracting. Is there a term that we can add or subtract from each side? Well, if we add 4 to the left and add 4 to the right, we can get rid of the negative 4. We will be left with A over 2 equals 12. Now we work our way down to the next set of options, multiply and divide. We can multiply each side by 2 to get rid of the 2 denominator, and we will have an equation that looks like this. The 2's will cancel on the left, and we have A equals 24. What about this? 23 plus 2 equals the square root of A plus 1. Before we start to work through our SAMDEB options, we might notice that on the left we could simplify things by adding 23 plus 2 to get 25. So we have 25 equals the square root of A plus 1. Now we'll look at our SAMDEB list. We can add or subtract a number from each side. If we subtract 1 on the right and subtract 1 on the left, we have 24 equals the square root of A. Now we can deal with the square root of A by squaring each side. And we are left with 576 equals A. What about this? 32 equals 18 minus x over 2. On the right-hand side, we are dividing everything by 2. The opposite of dividing everything by 2 on the right-hand side would be to multiply everything by 2. But if we multiply everything by 2 on the right, we must multiply everything on the left by 2 as well. Now, the 2's on the right will cancel each other out and we'll be left with 18 minus x on the right and 2 times 32 on the left. That gives us 64 equals 18 minus x. We'll move on to another option. We can add or subtract a term from each side now. If we subtract 18 from the right, we must subtract 18 from the left. And we get 46 equals negative x. But wait, we don't want to know what negative x equals. We want to know what x equals, so we're not done yet. We need to get rid of that negative sign in front of the x. How can we do that? We can multiply each side by the same value, negative 1. If we multiply by negative 1 on the right, a negative times a negative will give us a positive, and 1 times x is x. So we will have positive x. But if I multiply by negative 1 on the right, I must multiply by negative 1 on the left. And I get negative 46 equals x.
We don't have to follow the SAMDEB order in algebra.
It's just that often that's the easiest way to move terms around and isolate our variable. The next example will show a common mistake that can happen when we are solving equations with more than one step. And in this example, we will use a different order than SAMDEB. If you multiply or divide a term on one side of an equal sign, every other term on each side of the equal sign must be multiplied or divided by the same term. X over 2 plus 1 equals 3. If you decided to get rid of the fraction with the variable in this example, you would multiply by 2, since that's the opposite of dividing by 2. But you would need to multiply each term in your equation by 2 to keep things balanced. Each term is multiplied by 2. Let's see what would happen. Here's our equation, and this is what it looks like when we multiply each term by 2. Simplified, we get x plus 2 equals 6. We can subtract 2 from the left and from the right, and we get x equals 4. Let's check that answer. X divided by 2 plus 1 equals 3 was our original equation. We found that x was equal to 4. To check that, we can replace the x with the value in 4 and see if the left side equals 3, just as the right side says it should equal. When we put x equals 4 in for x, we get 4 divided by 2 plus 1. 4 divided by 2 is 2. 2 plus 1 is 3, so 3 does equal 3. We know we've done it correctly. Since we know that x equals 4, it helps us see that we went wrong when we seem to find that x equals 5 in this upcoming example. We get the wrong answer if we fail to multiply every term by the same value. X divided by 2 plus 1 equals 3. Multiply by 2, but we missed multiplying the 1 by 2. So what we would get in this incorrect example is x plus 1 equals 6. X plus 1 minus 1, subtract 1 on the left and subtract 1 on the right, would give us x equals 5. We have the line through the equal sign because we know that's not actually true. When we substitute 5 back into the original equation, we see it does not work. 5 goes in the place of x, which would give us 5 over 2 plus 1, which does not equal 3, because 5 over 2 plus 2 over 2 does not equal 3. 7 over 2 is not the same as 3. 6 over 2 equals 3. Remember why 5 is wrong. It's because we did not multiply every term on each side by 2. Finally, as this example just showed, in algebra, we don't have to wonder if we've done things right. We can always substitute the value we found for the variable back into the original equation. If the two sides are equal when we replace the variable with the value we found, we can know our calculations were correct.